I bet many of you are already very familiar with the Pythagorean Theorem, as seen here, which is used to describe the sides of a right triangle. There are many different ways to prove the Pythagorean Theorem, but in this video I will be using similar triangles. Take this triangle over here. The first thing we want to do is draw a perpendicular line from the right angle corner all the way to the hypotenuse. Here I've already drawn it out to make it look nice. We can see that we're splitting the hypotenuse, c, into two smaller values, c1 and c2. In other words, c1 plus c2 equals c, and we can write this as c2 equals c minus c1. This will come in handy later, but first, I can now split this triangle into two parts, a purple and a pink triangle. If I draw the purple triangle out, you can see that side B, which used to be a side length, now becomes a hypotenuse. Likewise, C2 becomes the lower side length. I've kept this green angle here so you can tell how I flipped the triangle around. Next, let's draw the pink triangle. Here, you can see that A, also a side length, has become the hypotenuse, and C1 is now the side length. In case anyone is curious, these triangles are actually to scale. Notice that the third angle in the purple triangle is actually the red angle. Likewise, the third angle on this pink triangle is the green angle. Now recognize all three triangles have the same angle setup: right angle, green angle, and red angle. This makes all three of these triangles similar to each other, which has many special properties. Most importantly, we can write the side lengths as ratios of each other. Here are the biggest takeaways from this relationship. Inspecting this first one here, notice that we are relating the hypotenuse to the side length of the first triangle, and the hypotenuse and the side length of the pink triangle. This gives us C over A, which is equivalent to A over C1. The second equality over here does a very similar thing. Take the hypotenuse of the first triangle and the bottom side length of the first triangle and compare it to the hypotenuse and bottom side length of the purple triangle. This relationship is C over B is B over C2. Now, let's perform some cross multiplication where we multiply the C and C1 and the A's together and the C and C2 and the B's together. I've already done that here. Notice that we were starting to form the very familiar Pythagorean theorem. However, we got these pesky C1 and C2 values, and we need to get rid of them. Since we're looking for something of the form a squared plus b squared, let's add them together. Using the definitions that we just derived, we got a squared plus b squared equals c c1 plus c c2. Now, take a moment to remember that we already defined c2 up here in this box. On the next step, we will replace the c2 with c minus c1. If you do that and distribute the c term, we will get cc1 plus c squared minus cc1. Something very nice about this is that these cc1 terms will cancel, and we will be left with the very familiar Pythagorean theorem. A squared plus b squared equals c squared. And there you have it. That is the Pythagorean theorem proof using similar triangles. I hope that makes sense, and thank you very much.